In 2012, a spacecraft launched during the Nixon administration crossed a boundary that no human-made object had ever reached. The signal took over 17 hours to arrive. When it did, it carried plasma readings that contradicted every model physicists had built over the previous 4 decades. This is what Voyager actually found, not the polished diagram version, the real, messy, surprising version. To understand what Voyager found, you first need a working picture of what it was flying through. And that picture is stranger than most people realize. The sun does not simply end. It exhales constantly, a stream of charged particles called the solar wind, blowing outward in every direction at roughly 400 kilometers per second. This wind carves out a bubble in the interstellar medium, the thin gas and dust that fills the space between stars. That bubble is called the heliosphere. Everything in our solar system, every planet, every moon, every comet, lives inside it. The heliosphere is not a perfect sphere. The sun moves through the galaxy, and that motion pushes the boundary forward on one side and stretches it into a long tail on the other, like a comet but on a solar scale. Voyager 1 flew out through the nose. Voyager 2 took a different angle and crossed the boundary further around the flank. That difference in paths turned out to matter enormously. Before either spacecraft could reach the heliopause, the actual outer boundary, they had to pass through a region inside it called the termination shock. Think of it this way. The solar wind is supersonic. That means it travels faster than the speed of sound in the interstellar medium. At some distance from the sun, that wind hits a wall of interstellar pressure. It slows abruptly, piles up, heats up dramatically. This is the termination shock, a standing shockwave billions of kilometers from the sun. Voyager 1 crossed it in December 2004. Voyager 2 followed in August 2007. Both crossings confirmed the shock's existence, but the measurements did not match what the models said they would find. The particles at the termination shock should have been heated evenly, protons and electrons gaining energy in proportion. Instead, the electrons were far hotter than predicted. The protons behaved differently depending on which spacecraft measured them. One spacecraft, one result. Different spacecraft, different result, at a different point on the same shockwave. It meant the termination shock was not smooth and uniform the way the textbook diagrams showed. It was irregular, dynamic. It moved. That single revision, the shock moves, changed how heliophysicists wrote every simulation that followed. Past the termination shock lies a region called the heliosheath. This is where slowed, compressed solar wind piles up against the interstellar wall. Before Voyager reached it, most physicists expected the heliosheath to be relatively thin, maybe a few AU wide. 1 AU, for reference, is the distance from Earth to the Sun, about 150 million kilometers. The heliosheath, it turned out, was not thin. Voyager 1 traveled through it for 8 years. 8 years of data from a region that barely existed in the pre-Voyager model. During that transit, Voyager's instruments recorded the magnetic field direction. And something was wrong. The solar magnetic field inside the heliosheath was not oriented the way any model predicted. It was tilted, rotated by roughly 40 degrees from the expected direction. That 40-degree difference carried real consequences. It meant the heliosphere's shape was wrong in the diagrams. And it told physicists that the interstellar medium pressing on the bubble from outside was also magnetized, and that magnetism was leaking in. Energetic neutral atoms were another surprise. These are particles that travel in straight lines. They ignore magnetic fields because they carry no charge. IBEX, a separate NASA mission launched in 2008, mapped them from Earth orbit using Voyager's traversal as context. IBEX found something Voyager could not, a bright ribbon of energetic neutral atoms wrapping around the heliosphere's flank. No model had predicted it. It is still not fully explained. Now we come to the heliopause itself, the actual edge, the place where solar wind stops and interstellar space begins. Physicists had argued for years about how sharp this boundary would be. Would it be a gradual fade or a crisp transition? Voyager 1 gave them the answer on August 25, 2012. The transition was sharp. In a matter of days, the flux of solar wind particles dropped to near zero. The density of galactic cosmic rays coming from outside jumped sharply upward. The magnetic field direction shifted, and it stayed shifted. Voyager had crossed the heliopause. At the time of crossing, Voyager 1 was about 121 AU from the Sun. That is 121 times the Earth-Sun distance. The light travel time from the Sun to that point, roughly 17 hours. When Voyager 2 crossed in November 2018, it did so at a different distance, about 119 AU, on a different part of the heliosphere. And crucially, Voyager 2 still had a working plasma science instrument. Voyager 1's had failed in 1980. This was the first time anyone could directly measure what the plasma, the ionized gas, was doing at the crossing point. What Voyager 2's plasma instrument found was a thin layer, about 100 kilometers thick, of extremely hot, dense plasma sitting right at the heliopause. The temperature inside this layer was roughly 49,000 degrees Celsius. That is hotter than the surface of the Sun. Nobody had predicted this hot layer. No model included it. The leading explanation now is that it forms from the collision of outgoing solar particles with incoming interstellar ones, a zone of friction where two different flows meet and release energy as heat. Two spacecraft, two crossings, 6 years apart, and both datasets told the same fundamental story. The boundary is real, sharp, and far weirder than the models assumed. Once past the heliopause, both spacecraft entered interstellar space. What does that actually mean physically? It means the particles around them are no longer primarily from our Sun. The gas is interstellar, ancient, low density, threaded through with magnetic fields oriented by the galaxy itself. The galactic magnetic field out there runs in a direction about 40 degrees off from the solar one, that same tilt that appeared in the heliosheath data. Voyager 1 measured the interstellar medium directly. The density of electrons, about 0.08 per cubic centimeter. A cubic centimeter, a space the size of a sugar cube. For comparison, the air in this room holds roughly 27 million trillion molecules per cubic centimeter. Interstellar space is not empty, but it is as close to empty as anything we have ever directly sampled. Voyager 1 also recorded plasma oscillations, vibrations in the electron density caused by solar outbursts passing through the heliopause and ringing the interstellar medium like a bell. NASA actually converted those oscillations into audio. The plasma wave team at the University of Iowa released the recording. It sounds like a low hum shifting pitch, the collective voice of electrons more than 20 billion kilometers from Earth. That data also let scientists measure the density of interstellar plasma more precisely than any indirect method had ever managed. Direct sampling from a spacecraft changed the number by a factor of 2. A factor of 2 matters in physics. It means the models were working from the wrong baseline for decades. Cosmic rays were the next chapter. Inside the heliosphere, the solar magnetic field partially blocks galactic cosmic rays, high-energy particles accelerated by distant supernovae. The heliosphere acts like a radiation shield, a partial one, but real. Once Voyager 1 crossed the heliopause, its cosmic ray counter spiked. The particle count went up by nearly 10%. That number matters for human exploration. Any future crewed mission to deep space will pass through this radiation environment. Engineers designing the shielding for deep space vehicles are now calibrating against Voyager's direct cosmic ray measurements, not models. Here is something that rarely gets mentioned in the popular coverage. Voyager 1 is technically in interstellar space, but it has not left the solar system. The Oort cloud, the vast shell of icy bodies that defines the gravitational edge of the Sun's influence, begins far beyond where Voyager is now. The inner edge of the Oort cloud is thought to be roughly 2,000 AU out. Voyager 1 is just past 160 AU. At its current speed, Voyager 1 will take roughly 300 years to reach the Oort cloud, and another 30,000 years to pass through it. So the heliopause is not a wall around a castle, it is more like the tree line at altitude, the point where one system fades and another takes over, while the mountain continues for a long way above. Now let's talk about what the Voyager data has changed in how we think about other stellar systems. Every star with a stellar wind presumably has its own heliopause equivalent, its own astrosphere. And if life exists around another star, it lives inside that star's protective bubble, shielded from galactic cosmic rays in exactly the way we are. The Voyager measurements give us, for the first time, a real number for what that shielding is worth. And they give us a way to estimate, based on a star's wind strength, how far its heliopause would lie, and whether a given exoplanet orbits well within it or dangerously close to the edge. Voyager's power source, plutonium-238 thermoelectric generators, is running down. NASA has been shutting down instruments one by one to conserve power. By the late 2020s, both spacecraft will likely go silent. When they do, they will still be out there, continuing at the same speed, heading toward different stars over tens of thousands of years. Voyager 1 is heading in the general direction of the constellation Ophiuchus. In about 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445. We launched a spacecraft in 1977. That spacecraft is now sampling interstellar plasma and telling us things about the universe that our best computers could not calculate from Earth. The boundary was not what we drew. The sheath was not thin. The shock moved. The hot layer was not predicted. The cosmic ray count was higher than the models said. Every single one of those surprises made the science better. That is how this works. You build a model. You send a spacecraft. The spacecraft contradicts the model. You build a better model, and you keep going. There is a concept in physics called ground truth. It means the actual data, not the approximation, not the simulation, not the clean diagram in the textbook. Voyager is the only ground truth we have ever obtained from the edge of the solar system, and it will be, for a very long time, the only one we have. The next mission proposed to reach the heliopause, the interstellar probe concept studied by NASA, would take roughly 50 years to get there, even with a Jupiter gravity assist. 50 years. The scientists who designed it will likely not live to see the data return. That is the timescale of this science. Decades of patience for hours of data that rewrite entire fields. What Voyager found at the edge of the solar system is not a single discovery. It is a list of things we had wrong and a few we had right, catalogued by a 47-year-old machine made of 1970s parts. The interstellar medium is denser than expected, hotter at the boundary, more magnetically complex, less predictable from the inside. And the heliosphere that shields us, that we live inside without thinking about it, is stranger, more dynamic, and more asymmetric than the clean bubble in the textbook. It is our home. We just have a much better map of it now. If this kind of science interests you, the real data, the real missions, the places where the models fail and the measurements win, there is more on this channel. Voyager is one thread in a much longer story.